So this is again continuation of the problem that we discussed in relative velocity method part 2. So due to some lack of time, we didn't complete the problem. So we will once again discuss the problem in detail. And I am Vijayalakshmi, Assistant Professor from Mechanical Department, DPGIT, Vellore. So we already discussed the problem where the lengths of the crank and the connecting rod was given, the angle made by the crank was given, and we were asked to find the velocity of the piston, angular velocity of the connecting rod, and velocity of a point E on the connecting rod from the gudgeon pin at a distance of 1.5 meters, and find out the rubbing velocity of the crankshaft, crank and cross heads when the diameters of the pin are given. So first, we draw the space diagram with the given detail. We draw the line of stroke, mark OB at an angle of 45, and the length of OB is given as 0.5. And by finding using the speed, that is NBO, that is 180 RPM, we find out what is the omega BO, 18.852 radians per second. Using that, you find out what is the velocity of B with respect to O, that is VB is equal to OB into omega BO. So we found out what is the velocity of the point B with respect to O. Now regarding the point B, the point B is rotating about the, whenever this is rotating, you can see the point B is, if you are considering the link PB, point P is going to rotate about the point B. So velocity of P with respect to B will be perpendicular to PB. And if you are considering the point O, velocity of the point P with respect to O will be along the line of stroke. So velocity of PO will be along the line of stroke and velocity of PB will be perpendicular to PB. And velocity of BO will be perpendicular to the crank. Since the crank makes an angle of 45 degree, its perpendicular will also make an angle of 45 degree. With the given data, we will try to draw the velocity diagram. First, let us fix the fixed point O. After fixing the fixed point O, we can mark the velocity of B with respect to O. So we know the magnitude of VB is 0.9426 and it's making an angle of 45. So you mark the velocity vector VPO. We know that the velocity vector VPO is perpendicular to PB. So in the space diagram, we draw a perpendicular to PB, find out the angle that it is making with the horizontal, and that angle you can mark it here. So with respect to starting from P, this will be the direction of PB. And you know that OP will be along the horizontal line. So this is OP. So these two lines will intersect at a point. So that point is the point P. So if you want to find out the velocity of the connecting rod, if you measure what is PB, that will give the velocity of the connecting rod. So if you want the angular velocity of the connecting rod, the velocity vector divided by BP will give the. So if you are measuring PB, that will be the velocity of the connecting rod. If you are measuring OP, that will be the velocity of the piston. So by measurement, we can find out the velocity of the piston is 8.15 meter per second. Now to find out the velocity of the rubbing. We know that the diameter of the crankshaft pin at O is equal to 50 mm. Diameter of the crankshaft pin at B is equal to 60 mm. Cross head pin is DC, that is 35 mm. So velocity of rubbing at the pin of the crankshaft is equal to omega BO into the radius. So at the pin of the crank is equal to, it is connecting the connecting rod as well as the crank pin. So omega of the connecting rod, that is PB, and omega of the crank into R. So they are going to rotate in the same direction, opposite direction. So you take it as positive. Okay. So velocity of rubbing at the crosshead is again, crosshead is nothing but the connecting rod. So here the slider will not rotate. So only the connecting rod will have the angular motion. So you have to just take the connecting rod angular velocity into diameter of the crankhead. So if you substitute all these values, you can find out the velocity of rubbing. So this process is relatively simpler when comparing with instantaneous enter. Both methods are equally simple. Okay. So thank you.